Okay, welcome to the second video on guide sheet number 4. We're just going to start with a quick review of refraction and which way the light will bend. Again, it's always from slower to faster, it moves away from the normal. If it goes from faster to slower, it'll move toward the normal. So more optically dense is slower to faster, so this first one must bend away from the normal. Less optically dense is faster to slower, so this bend had to be down toward the normal, so that means this first one had to have a steeper angle, something along that line. Now the actual amount, we'll see that next in Snell's law. Medium one again is more optically dense, so it's more optically dense means it's slower, so this must have bent away, so this angle must be less steep than the first one. And again, these angles are always measured from the normal, not from the boundary. Light travels fastest in medium number 1, so it's faster to slower, so it must move toward the normal, must bend toward the normal. Light travels slowest in medium 1, so it's traveling slower to faster, so it must bend away from the normal. Here's where it would go if it wasn't being bent, so it has to be something steeper where this angle increases. Light travels faster in medium number 1, so that means it travels slower over here. Slower to faster, it's going to move away from the normal, so that means that this one again has to be less steep, although I need to draw it in the other direction. Okay, so it looks something like that. So a smaller angle, steeper angle, measured from the normal. Okay, now Snell's law is what allows us to actually measure the value of the angle. It's credited to a Dutch mathematician, Willebrord Snellius, back in the late 1500s, early 1600s. Although it was actually found out earlier, it's just he got the credit. It says that the relationship between the index of refraction N1 and the index of refraction N2 for two different materials, which we know is directly related to the speed of the material, of light in that material, is the relationship that holds. It's actually a ratio of the sines, not a direct relationship of the angles themselves, but of the sines of the angles. Okay, so if we have a situation like this on the right, if this is our theta 1, that's again called the index of the angle of incidence. There's theta 2, that's the angle of refraction after it's gone through and refracted. N1 is the index of refraction for the first material, N2 index of refraction for the second material. V1 is how fast the material light moves in that material. V2 is how fast it moves in that material. When you're trying to get these two angles, the most common configuration of Snell's law to use is that N1 times sine theta 1 is equal to N2 times sine theta 2. Okay, so we're going to apply that down here to a couple of situations. So N1 sine theta 1 equals N2 sine theta 2. Now an incident ray in air, so this is going to be N1, is approaching the boundary of the unknown material at an angle of incidence of 61.6, so that's theta 1. And then the index, the angle of refraction, that's theta 2, is 41.4 degrees. We're going to try to figure out the index of refraction of the unknown material. We're going to try to figure out N2. So if I solve this equation for N2, it's going to be equal to N1 sine theta 1 over sine theta 2. So it's going to be 1, which is the index of refraction of the air, times the sine of the angle of incidence, which is 61.6 degrees, and the sine of the second material, which is 41.4 degrees. Okay, so we can then go ahead and calculate that. Sine of 61.6 divided by the sine of 41.4. Do be careful with your parentheses if you're using the TI family of calculators here. Don't forget to close that parentheses off right there. And that's 1.78. Let's see, we have two significant figures roughly here. It looks like maybe three. So 1.78 would be the index of refraction of the new material. Now we could then go to a reference source and look up what type of material that most likely is, because every material has its own specific index of refraction. Part B, an incident ray in air at n equals 1.0 is approaching the boundary with glass n equals 1.52 at an angle of incidence of 32.5 degrees. So this is 32.5 degrees. This is n equals 1. This is n equals 1.52. We're going to try to figure out what the angle of refraction is. Now, since it's going from faster to slower, it will bend toward the normal. This is the angle theta 2 we're trying to figure out. Okay, so we're going to solve the above equation, Snell's law, for theta 2. So we're going to take n1 sine theta 1. We're going to divide that by n2. Now that will tell us the sine of theta 2. So to actually get theta 2, we're going to need to take the inverse sine of that ratio, and that'll give us theta. So in this case, we were talking about, now n1 is 1, so we're taking sine theta 1, sine of 32.5 degrees, and we're going to divide that by the index of refraction for the new material, 1.52. Okay, and then we're going to go ahead and take the second function, inverse sine of the answer, and we get 20.7 degrees. So the new angle theta 2, and this is theta 2, is equal to 20.7 degrees. Now that is smaller than the 32.5 as we had planned it, said it should be, so that seems like a reasonable answer in this case. Okay, so I've got a couple of different situations down here, and you should go ahead and see if you can figure out the angles of the second waves. The information you're going to need is the angle here is 45 degrees, so you can measure that right on your paper. This one's 60 degrees. The index of refraction for ethanol is 1.36. That for diamond is 2.42. And then figure out the angles of the refracted ray. So when you're ready, pause that and go ahead and do that. Down here, again, you can measure them for yourself, but the angle here is 45, 17, 17, and these are all in degrees, and 45. The index of refraction of the air is 1, so you're going to try to figure out the index of refraction of the block of material. You'll be doing a very similar lab to this next class, so hopefully you can figure this one out. You're going to do the calculation twice, once for the incoming and then once for the outgoing. You should get the same value since it's the same material. You should get the same value for both. So go ahead, pause the video and take a few minutes to do those, and I'll put the answers up for you and you can see how you did. Okay, so for the first one you should have gotten 54 degrees. It's going from a slower substance, glass, to a faster substance, water, so it had to turn away from the normal. Had to be greater than 45 degrees. It turned out to be 54. And the second one is going from a slower to a faster to a slower substance. The n is smaller to a larger. Diamond's actually got a very high index of refraction, so it's bending all the way to 29 degrees. In the second one, you get the exact same solution no matter which direction you go. If you start at the top, you get 2.42. If you start at the bottom, you get 2.42, which is also the index of refraction of diamond. So that would indicate that this substance is diamond. So one of the ways you can identify what kind of substance is in some material is to run light through it and see how much the angle bends and compare it to known measurements. Index of refraction. All right, so that's the fundamentals of Snell's law and refraction. We do have a lab to cover on measuring the refraction of light as it travels through a block of glass, and then we'll be done with that.